Hi there, welcome back to the course on understanding retrieval-augmented generation. We're not really talking about RAG yet, but we need to learn the basics of information retrieval. So in lecture one, we talk about the most basic way of building an information retrieval system, boolean retrieval, and now retrieval, which is very important for RAG. So what's the problem with the Boolean search that we have seen earlier? As we mentioned, it's very good when you need to find something on your computer or in your mailbox, but then when you're doing like a web search that you don't know exactly what to expect, then it's not good. And here's an example of that. Let's say my query is standard user d-link 650, and I get 200,000 hits. What's the problem with that? That's why it's called feast and famine. Even in the feast case, it's not good because these results, they are not ordered from the most relevant to the least relevant, right? We haven't devised any ranking system just yet. That's what we're going to do in this lecture. So I get these 200,000 hits and I don't know how to reorder them, like which one is more important than others. So it's too much information, literally. So what can I do? I can revise my query, add a few keywords, and then I get 0 hits because it was too specific. So that's not good. I want something in between. That's why I need these documents here to be ranked from most relevant to least relevant. So this is what rank retrieval is all about, and this is also how the initial Google search algorithm worked on top of course, looking at links between web pages. And this is really important these days because most people don't go past page one of Google search. And even when we'll talk about RAG, this is even more important because in many cases, RAG only uses the top one result. So having this ranking scoring system put in place properly is very important because again, uh, users these days are very spoiled. That's why at Google, they used to say the best place to hide the dead body is page or page one of Bing. So we don't want the feast or famine situation. That's why we're going to come up with some scoring, some ranking for our documents, and then we're just going to get the top K, the top 10, or even the top 1 in the case of RAG. So how do we come up with this score? It needs to be a score that goes from 0 to 1. 0 is easy because it means an irrelevant document. The problem is how to get enough nuance between 0 and 1. So we are looking for a floating point score, basically, from 0 to 1, where 0 is not relevant, 1 is very relevant, and anything in between. So again, the 0 is easy, it's no relevance, and it's the same 0 that we were using in the Boolean system, right? When a word is not in a document, the score is 0. Now, how can we add on to this in the case of 1? How do we go from 0 to 1? We could be using some coefficients like the Jacquard coefficient that we'll talk about in next lecture. But these are still not very good because then they don't really tell me about the frequency of words in a document. So for example, if my query is cats, I want to find all the documents that are relevant to cats and ranked from the most relevant to the least relevant. What can I do? Can I count how many times the word cat is present in this document? That's a good idea. But then I also need something else. I need to know how special this word is in my document collection. That's why we also talk about document frequency. So we need something that finds the best trade-off between term frequency and document frequency. That's why a metric like Jacquard coefficient is not good, and we come up with this new score that it's called TF-IDF, exactly from these two items here. TF is term frequency, IDF is the inverse of the document frequency. Okay, let's see how to calculate this TF first. This is the matrix that we were using earlier, the Boolean matrix, where one encoded presence, which meant that even if, for example, the word Anthony is present many times, as it surely is in the play of Shakespeare entitled Antony and Cleopatra, I only put one, while 0 means that the word is not there at all. So the next step is to have a count vector. How many times each word appears in each of these places? Oh, now we are talking. Now we can see which documents are more relevant to a specific word. I can see that, for example, if my query is Caesar, then Antony and Cleopatra is slightly more relevant than Julius Caesar because the word Caesar appear more times than in Julius Caesar itself. So this is good, but it comes with two problems. First of all, it doesn't tell me how special each of these words is in my document collection. And number two is a bit too much to use the frequency. Why? Because then if a word appears in a document 10 times versus one, it's not fair to say that it's 10 times more important, right? But still, the 0 is the same as before. So the 0 means that the word is not there. And now we still have some ones, but these ones means that now the term, for example, worser, is present in the play The Tempest only once. So 1 is not encoding presence anymore. It really means that this term is appearing once. So it's called bag of words model because it's really like a bag of words. We are not encoding any sequence, any context. This is what word embeddings do, remember from the previous course. And this is a problem because then we have things like free alcohol versus alcohol-free that mean the same thing in a bag of words sense. So this seems like a step back, right? We were looking at positional indexes in the previous lecture, but we'll look at recovering this later. Now we really need to understand how to come up with this score. So again, I already said this, if my query is cats and document 1 contains the word cat once and document 2 contains the word cat 10 times, is it fair to say that document 2 is 10 times more important than document 1 when I present my result? It's not, right? It's too much. That's why we're using that beautiful logarithm function that we talked about earlier. Why? Because it's one of those nice functions that slowly grows. And this allows me to do things like this. For example, if a document contains the word 10 times more than another, is only twice as important as the other document. If document 2 contains the word cats 1,000 times more than document 1, then it will be 4 times more important. So I like this. This makes more sense. It's not fair to say that it would be 1,000 times more relevant. So I'm using the logarithm of TF, given the term T in document D. And this is just a little problem. The logarithm function is very beautiful, but it goes to minus infinite at 0. So we only want to look at the part that comes after the 1, right? That's why we are doing 1 plus the logarithm of TF. So in some books, the notion of TF is different. In some books, you find that it's the logarithm of 1 plus TF, but we're going to be using this one instead. 1 plus the logarithm of TF. Of what? Of the terms T that are both in the query and in the document. So this is important. We'll talk about this again later. There is no point to calculate this score for those terms that are not both in the query and in the document, right? Because eventually it will be 0. Now we just need one more bit to define TF-IDF, which is the IDF. IDF stands for inverse document frequency. What is the document frequency? It tells me in how many documents in my collection a word is. So if I have a term like arachnocentric, it's quite special, it's quite rare, and I expect it to have a very low document frequency. What does it mean? That maybe it only appear in 1 or 2 out of 100 documents. So this is a good bit of information to have, having the document frequency. But so we have the same problem as before. We want to dampen it with the logarithm, and also we want to take the inverse, right? I'm trying to measure the rarity. The document frequency tells me how frequent is a word in a document collection. So that's why we define IDF like this: is n, the total number of documents, divided by df of t, of the term t, where df again is and how many documents contain that term t at least once. And then I'm ready to build my TF-IDF score. The base of the logarithm is immaterial. I can use 10, I can use E, I can use whatever, as I did for TF. We'll see later that sometimes IDF can be excluded, and this is true for situations like when you have only one-term queries. This is interesting to understand really what's the role of IDF. When I have a query that is made of more than one term, it helps me to understand the query should I focus more on. So if my query is just cat, I don't need the IDF. But if my query is curious cat, then I need the IDF to understand whether I should be focusing more on curious or cat. The last bit to highlight is that document frequency is not collection frequency. So again, when I calculate the IDF, is the inverse of the number of documents that contain the term T at least once, which is different from the number of times that term appears in my document collection. So what does this mean? Let's look at two terms, insurance and try. In terms of collection frequency, they are the same, which means that they appear about 10,000 times in all my documents taken together. I'm literally just counting how many times I encounter these two words. But their document frequency is very different. This is the number of documents in which they appear at least once. So there's a huge difference. This is really telling me how rare this term is, like insurance is rarer than try because it appears in less documents. So this is exactly what we are after for our beautiful TF-IDF score that finally looks like this. 1 plus the logarithm of the term frequency multiplied by the logarithm of n, total number of documents, divided by the df, the document frequency. You can find TF-IDF or with the hyphen or with the multiplication symbol, so but it's still the same thing. And this is the final thing that we need. We need, remember, given a query, we need to have a bunch of relevant documents scored from the highest, most relevant to the least relevant. So given a query Q, for each document D, we will have to calculate this score. How? We use the TF-IDF formula that we just saw earlier, and we sum all the TF-IDF score together for all those terms that are both in the query and in the document. So if this sounds a bit confusing, don't worry, because we'll do some exercises on this. But before that, I need to specify what's the smart notation and the different variants of TF-IDF. So the standard form of TF-IDF is this one in red, which we just mentioned, which is also known as LTC. L stands for logarithm, T for the use of IDF, and C for cosine. So these are all variants that I can mix and match. So for example, LNC would be a TF-IDF score that does not use the document frequency, see? And an ATN would be one that uses augmented term frequency, the IDF and no normalization. What is normalization? We'll see that later. But so how do I specify this a priori? I use this smart notation ddd.qqq. DDD tells me which of the variants I'm using for the document, and QQQ tells me which ones I'm using for the query. So a notation like this, lnc.ltc, means that I'm using the lnc variant for the document and LTC for the query. Okay, let's take a break and let's look at an example. So I have this one document and this one query, and I have to calculate the one score that I will use then later to rank this document together with others. What do I do? So here I take all the words that I've seen in this two documents, auto best car insurance, but actually, if you remember, the formula said that I only have to take the terms that are both in the query and in the document. And here I'm not doing that, right? I'm also taking auto and best, and that's sort of a mistake because auto is not in the query and best is not in the document. But no problem, because in the end, guess what? The total addendum that I will need to use to then calculate the score is 0. But still, I wasted some time doing all these calculations for nothing. That's something to remember to save time. So first of all, I'm only interested on the terms, in this case, car and insurance, that are both in the query and in the document. So what do I do next? First, I need to calculate the TF-IDF score for the query and then for the document. And I'm given the smart notation lnc.ltc. So TF is 1 because insurance only appear once in the query. So 1 will be the logarithm. And the document frequency is given to me. This means that the word insurance appear in 1,000 documents in my collection. IDF will be the inverse of this, and then the TF-IDF score, I just get it by multiplying my IDF by the TF. I get 3 as the TF-IDF, which I want to normalize. So what is normalization? I'm just dividing by the L2 norm. We'll talk more about this later. For now, just think of it as a normalization factor. I'm just looking at the length of the document and dividing each of these terms by the document length, which in this case is 1.92. Why do I do this? So that instead of having these numbers that some are big, some are small, I have all these reduced into the space of 0 to 1. So this is much easier for me to understand, to compare different items, right? Anyway, we'll talk about this later. Now the point is there, I calculated the normalized TF-IDF score for insurance. I can do the same for car, but then I'm not done. I need to do the same for the document. The document slightly easier because I'm using the LNC variant of TF-IDF. And so this is how eventually I get to my two scores. What do I do next? I need to multiply them together. 0.52 multiplied by 0.52 gives me 0.27. 0.78 by 0.68 gives me 0.53. What do I do with this? Remember, the formula said that I have to sum them up together, and this is exactly what I do. 0.27 plus 0.53. And also the first two, which, by the way, were 0. So here you see why we only care about the terms that are both in query and document. So this is a simple yet powerful exercise because it really shows you how to calculate the score, the TF-IDF score, for a pair query document. So if you don't know how to do this, try again or do some of the tutorials. So this is what we did so far. We started from the Boolean model, then we started using the count vector, and then finally we have a weight matrix where everything is a TF-IDF score, right? Which in this case is not normalized, but if I normalize, I'll have all these in between 0 and 1. And this is something that is very useful to represent any kind of items in computer science, documents, images, videos. This is what we discussed in the previous course. Once I have built my multidimensional vector space where the dimensions are, in our case, the number of words, I can represent as arrows or points all these vectors in this space. So I do the same for the query as we've just done for the exercise. And then by calculating how close each query is to each document, I can then come up with this ranking score that then I use to rearrange the documents from most relevant to least relevant. So the last question to answer in this lecture is, how do I calculate this distance or similarity? So we could use the Euclidean distance, which calculates the distance between 2 points. So in 2 dimensions, it would be simply the Pythagoras theorem, right? So why is Euclidean distance not a good idea? We actually discussed this also in the previous course, because if I have a query like this that is maybe jealous gossip, the most relevant document would be D2 because it contains an equal amount of terms gossip and jealous, but then because the length is so big, when I calculate the Euclidean distance between this and that point, I actually get a bigger distance between these two than the rest of the document. So that's why we said we want to look at the angle between these two vectors. And we explain this by copying D into itself, D prime, and this really shows how to calculate the similarity, because these two, semantically speaking, should be the same, but when I calculate the Euclidean distance, they are not. Instead, if I look at the angle, it's 0, and so that's good. So let's not get confused. Euclidean distance tells me how dissimilar 2 points in space are, while the cosine similarity tells me how similar. So the bigger the cosine similarity, the better in terms of how similar two documents are, or how high the ranking should be. Why do we choose cosine out of all angles? It's just a standard. It's because it starts from 1 and it slowly goes down to 0. The L2 norm is what we use for normalization. This is an important bit so that the length of those vectors, of those documents, doesn't affect our calculations. So again, you can see this when you copy a document into itself. The length changes, but the content of the document doesn't, right? And this is also important in terms of calculations, because the original formula to calculate the cosine similarity between two items, Q and D, in this case, query and document, is this big formula. But if I normalize my vector space first, then it's simply the scalar product. Dimension by dimension, I just do a multiplication and then sum everything together. So this is important. Even if, let's say, I want to use Euclidean distance, it would still be important to normalize, because then you see, even if I use Euclidean distance here, then things still work. So the recommendation is to always apply normalization, no matter if you're using Euclidean distance or cosine similarity. Now, mostly we talked about information retrieval. So given a query, give me a ranked list of relevant documents. But these are tools that we also can use for other applications, like, for example, recommender systems, because this basically tells me what is similar to what else. So let's say that I read the novel Sense and Sensibility, and I really liked it. And I want for my next novel to read something that is as similar as possible. So which one should I choose? Is it Pride and or is it Wuthering Heights? So I'm not asking someone who actually read these novels. I'm building, once again, a model that I can use to make this kind of decision. So how do I do this? I use the count vectors. So for each term, in this case, to keep things simple, we only take 4 terms. So we have our 3 novels. We count basically how many times each term appears in a novel. And then we apply our TF-IDF scoring. So 1 plus the logarithm of the term frequency give me 3.06 after normalization, because again, I don't want to have all these numbers that goes from 1 to 2 to 3. After I divide for the L2 norm, I get all these nice numbers that are between 0 and 1. So, for example, the normalized affection of Pride and Prejudice, how do I calculate that? I take 2.76 divided by the L2 norm, which is the square root of 2.76 elevated to the power of 2 plus 1.85 elevated to the power of 2 plus 0 plus 0. This is the L2 norm or document length. So once again, I'm dividing by this to normalize and have all nice numbers in between 0 and 1. So what do I do next? Now I finally have this beautiful 4-dimensional vector space with 3 data points, and now I can use, for example, cosine similarity to decide which is similar to which. So my initial question was, which novel is Sense and Sensibility more similar to? I have to calculate the cosine similarity between this and Pride and Prejudice and Wuthering Heights. How do I do that? Apply dimension by dimension, remember scalar products, and sum up all together. So in this case, it would be 0.789 multiplied by 0.832 plus the second dimension plus 0 plus 0. So the total score is 0.94, which is good because the maximum similarity is 1, right? So that tells me that Sense and Sensibility and Pride and Prejudice are very similar, more similar than Sense and Sensibility versus Wuthering Heights. So again, this is a very powerful way of representing data and perform analogy, calculate similarity between data points, documents, images, videos. And again, this is how 90% of computer science works. So to summarize, what we did is, first of all, we came up with the definition of our TF-IDF score. Then we use that to represent all our documents in our document collection. Then, given a query from the user, we also represent that query as a vector. And then I calculate the cosine similarity between this query Q and all the documents in my document collection to come up with and scores that I use to rearrange my document from most relevant to least relevant to the query, and then maybe just take the top 10 to provide to the user as the top 10 most relevant documents to the query. So I hope this was clear. There is this nice video that nicely visualizes what we just talked about. You can take a look when you have time. I want to leave you with one last thought, the fact that this representation and these techniques that we saw, despite quite simple yet powerful, they still have the limitation that they don't define any of the things that we are working with unless we define those documents by the words that they contain. So again, this can be useful to calculate the similarity between data, but it doesn't tell me what each data point is. I can represent jackfruit as and a durian as vectors and see that they are very similar to each other. But if I don't know what at least one of them is, then I wouldn't know what to do with this similarity. So this just to say that there's much more to intelligence. This only emulate one kind of reasoning, analogy-like reasoning, analogical reasoning, but there are many other kinds of reasoning, as we've seen in the previous course, like inductive, abductive, common sense reasoning, and so on. Okay, that's all for this lecture. Let me know if you have any doubts, and if not, I'll see you in the next lecture. Ciao.